talk too far. So previously was wonderful talk, and Sharon started mentioning that one of the difficulties is how do we represent deformables, how do we do state estimation for deformables, and this in part is what I'm going to address there, and then I'm going to talk about the scalable simulations and the real sim in that context. Oh wow!
Sorry for interrupting.
Okay, so I have additional equipment here. Oh, all right. So I'll try not to shout. So yes, so we're going to first look at the challenges with representing deformable objects. Then I'm going to talk about our approach to this, which is a distributional representation for deformables. Then I'm going to talk about what is real to sim for deformables and can we do it with these new things that are called differentiable simulators and what are the challenges there. And because we have some challenges there, we can also step back and go and see a little bit what still is there to be done with the non-differentiable black box simulators, but at scale. So this has been brought up many times during this workshop that we have potentially an infinite number of degrees of freedom as compared to what we have with rigid objects, that is very hard to obtain full supervision for deformables, and you know that some equipment exists for producing this, but it's very labor intensive, equipment is very expensive. So we need to be able to develop self-supervised and unsupervised methods that can handle this. Moreover, as we probably all know, the occlusions and the high deformability, they make the states of the deformables look very, very different depending on not only the perspective as you would have in the rigid object, but also kind of the time step and how the object deforms. And then usually when people face these difficulties, what they would say is, okay, well, how about we embed our high dimensional challenging state into low dimensions, and great, we can, you know, do model learning or policy learning, but in this low dimension. And what I'm going to be observing here is that the challenging dynamics, they remain in the low dimensional space as well. So tracking what is happening to the object, even if you were to embed it in the low dimensional space, would be challenging. So you can have low dimensional spaces which are hard to represent, but here is one example which is easy to represent just in the picture, which is you extract a bunch of key points. And if you use supervised or unsupervised key point methods, at a certain point in time, if you have a lot of deformation, you will have challenges and you will not be able to, let's say, track the key points across time, and there will be issues with noise as well. So we need to cope with ambiguous representations for deformables, even if we are able to extract a low dimensional state with them, and we need to be able to cope with noise. So our approach here is to use unsupervised methods that can help us reduce the dimensionality first, but then put distributional state representation onto the resulting low dimensional state, which is represented here by key points. So after we extract the key points from, let's say here an RGB image of a deformable moving, we interpret this as a sample from the probability distribution, and this probability distribution encodes the actual state of the object. Why would we want this? So one is this distributional view allows us to have permutation and variant representation. So we no longer have to really keep track of the correspondences of these key points. And for many of the applications, this would be favorable. So dropping this need to track the key points through time. And then we can also show that we would be more resilient to occlusions and noise with this paradigm. So now just to scope this term, real to sim, what does this mean? So suppose we have this example of just a robot flinging up a small piece of cloth in the air, and you can see that depending on the properties of the cloth, it would land on a table in a different way. So the real to sim problem is to infer the physical simulation parameters so that the simulated objects, they behave similar to the real objects. So of course we can change something about the friction and scale, but also here in this work, we would look at changing bending stiffness and elastic stiffness. And ultimately you can change any parameters that you have available for you in your simulator. And I would notice here that with even a small change to some of these parameters, you drastically change the outcome of the shape of the end state of the object. So that's why it's a challenging problem. All right. So just to prepare us as to what sort of hardware examples we would have with this, something like rope winding, flinging cloth in the air, maybe not as dynamic as what we saw in the previous case, but still, the cloth deforms under gravity, so you can't really full control its motion. Then some household tasks, like for example, wiping. And here again, you can have a cloth. Here is a pretty stiff cloth that doesn't deform, but you can have much more deformable cloth as well. And here's an example with a 3D deformable, which is kind of like a tire or a hoop object. And you can have various things like, for example, assembling a belt and pulley system is an inspiration for a task like this. So we have a simulator. In this case, this is just a bullet simulator that is stylized to resemble our physical setup. So, similar colors and similar colors for background and for the object, as well as in reality. And we're going to be changing the bending stiffness, elastic stiffness, friction, and scale parameters. Again, the method is general. You can be changing any properties of the simulation. But here I've shown that already with these parameters, you can see very drastic changes in how the deformable behaves. So we're going to take a look at how we could handle that. So overall, I'm going to be talking about the method that we named ReSim RKHS, and I'll explain overall the overview of this and the distributional representation for deformables. That is a key part here. So at first, we sample from what I would call a prior on the simulation parameters. It could be some uninformed distribution over, like what are your initial physical properties of the simulator. Then we extract the key points. There are several methods in the literature that can do it. There are some supervised, some unsupervised, but here we're not particularly demanding to what this method should do. It should just sample the key points on the object, doesn't matter where. And then we pass this through an RKHS net layer, and I will talk in detail what this means. So here we take the key points that are unordered, and they can appear on various parts of the object, and we interpret this as noisy samples from a partially observed state distribution. And so what we do with this is we embed this into an infinite dimensional space that I'll explain. And this is in order to get, as I mentioned before, permutation invariance and robustness to noise, but also a convenient distance metric. So we will be able to kind of mathematically compare the different states, how close they are to each other, and various nice properties such as the continuity of this metric and this representation. So ultimately, we're going to be relying on what is called the kernel mean embedding. And this is something that would help us to map the, find the embedding map into this infinite dimensional space. And we can represent the probability distributions in this way without the loss of information. Effectively without the loss of information. And what I mean here, and here is some literature for people who are interested in the mathematical aspect of it, is that with this mapping, we can recover the expectations of all the functions in a given space, in a given reproducing kernel Hilbert space, via a dot product. So if we have our mapping that we're looking for, and we have some function that we're interested in, via a dot product, we are going to be able to recover the expectation of this function. So this is ultimately, could be useful for various reasons. So what we have here is a previously existing nice mathematical structure that we can work with. And so what we're going to do is this is, okay, now we, from math, from theory to practice, we're going to apply this to, okay, what happens if we actually have key points? These are a finite number of samples of our probability distribution that we don't observe of the deformable object. So first of all, we're going to convert this, abstract embedding into an empirical embedding with IAD samples. And so this just means that we're going to be treating our key points as just samples. And then with that, we could use various kernel methods in order to do the embedding. But if you're familiar with kernel methods, you would right away bring up the problem that they tend to be computationally demanding. And so anticipating this, because we want to scale right away, we're going to take an approximation with random Fourier features that will allow us to compute various functions that we need in a pretty fast manner. So what does this mean? This means that we can approximate the kernel distances, which would otherwise be computationally demanding to compute, with a dot product of two feature vectors. And these two feature vectors would contain pairs of cosines and sines with some parameters in them. And I would like to briefly explain this just from an intuition perspective. So what this effectively does is this introduces a choice for projecting onto different dimensions. So because we're mapping into an infinite dimensional space, we're not going to be able to say, put a coordinate system and just like cover all of them. There's an infinite number of them. But we randomly choose in which direction. So like this wiggly function here sort of represents the functional direction onto which we're projecting. And so you can think of it as building a coordinate system with a finite number, so basically like a finite subset of overall number of directions. Right, and here we would have some parameters like this W vector is kind of like where this direction is pointing, and we have an additional parameter which controls the stretch of this overall. And so this is how we are going to use the approximation in order to make it very computationally efficient to map these key points into effectively an infinite dimensional space, but then still have a finite dimensional representation for this that is computed quite quickly. All right, so this is our RHSNet layer. And the interesting part of it, because in this day and age we do everything with deep neural networks, is that the reason why we call it a layer is because we can insert into any neural network whatever you like, and we can propagate through this layer the gradients. So whatever end-to-end system you're going to plug it in, it's going to propagate the gradients and going to be able to adjust these sigmas and w's, so like these directions and stretches that I've talked about before, effectively making it more, making this coordinate system choice more adapted to the data that the system is actually training on. All right, so we're done with building this layer. Now we're going to put it into this overall system and continue building it. So after we have this layer, we're processing our key points. We're mapping it into infinite dimensional space, but with this approximation. And then the output of this basically presents for us like this new transformed state of the deformable. And you can add to it the overall state of the other system. Like, for example, if you're tracking your robot, where your robot is. And then we're going to train something that has been introduced before in RSS 2019, a method that's called base sim, which is going to take the input simulated trajectories. So by trajectories, I mean this data that we have just encoded, maybe padded with where the robot is, right? So a representation of deformable and then the robot. And what it's going to learn is going to learn the mapping from the input simulated trajectories to the output of the Gaussian mixture of simulation parameters that have generated these trajectories. Because we're just doing this in simulation, right? That both this input and output is available to us. And then, so the training is just going to be done with data of likelihood. And this is just like a regular training of a mixture density network, just with these special inputs and outputs. And then after this, we're going to infer the posterior for our simulation parameters by passing through this network the data for the real trajectory of what happens when the real robot manipulates this deformable. And then what would happen is we would, over time, so let's say we have one trajectory, but we could have multiple trajectories, we would be able to get from this mixture density network the mixture distribution of what our simulation parameters should look like, but the distribution of them, not a single point estimate for the parameters. And that is supposed for us to produce all the multitude of simulated trajectories that most resemble the motion of what happens in this real demonstrated trajectory. So that's our overall system. And what I would like to show now is, okay, what is this useful for? So here is an example of the key points extracted with an unsupervised key point method. And these plots show the distance to the ground truth state. So here the ground truth we're comparing the state of the deformable by kind of like the region of the space that it occupies. And here this ground truth, we're calling it ground truth because this is not available to any of the methods. We're not training with it. We're just like post factum looking at where the deformable object is and creating the mask curve and comparing the masks. All right, so this is our evaluation metric. And on the plot here, we're comparing base sim, so this approach of inferring the posterior for the distribution of the simulation parameters with the original inputs. So these are just the raw key points compared and various other features that could be extracted from that. And comparing it to this base sim RHS and base sum RHS, two variants which are using our representation of this embedding into an infinite dimensional space with approximation. And you can see here a pretty large difference. So we can get to the ground truth much quicker, and we're able to do this not only for this unsupervised method, but also for the supervised extraction method. So here are the key points that are obtained with a supervised approach, also a little bit noisy in this case. And likewise, we can get a fairly good improvement in performance here compared to base sim with other representations. Also compared to methods which I call bulk methods, which instead of iteratively estimating the posterior, they're just getting a bunch of data, training some simple model, for example, like an MLP, or training a Gaussian, fitting a Gaussian process with a Gaussian regression, Gaussian process regression, and then outputting, the estimate for the posterior for the simulation parameters. So we can do this with a few objects in the scenarios that are shown before for this Fling task, where we're tracking the state of the cloth with the key points. But again, these key points don't have to be systematically placed on any part of the deformable object. Then these are examples with the wiping task. And likewise here, this blue and black line, you can see that we're getting some performance improvement here as well. Then this is this task with the hoop. And here I want to highlight that you can see that the key point method has in part failed to track the motion of the deformable, and there's like some pretty visible noise here in the case of the unsupervised method, and we're still able to benefit from it compared to not using our representation. All right, so with this, we have a method that can do inference for the real-to-sim problem for inferring the physical parameters for deformables. And we can do it from either a single real trajectory, or we can also adapt to the changing dynamics if we, for example, use this method iteratively and we feed new data with a slightly changing situation. And this is all ready to use as adaptive domain randomization for now sim to real task if we wanted to close loop and go real to sim and then sim to real. All right. And so transitioning to, okay, what else can we do for the real to sim? Is this the only thing? These days on our minds is the fact that, okay, these black box simulators where we don't have any gradients going through the simulator itself, okay, they're interesting, but they need some data generation part for us to be able to do something with them. So what can we do? We can use differentiable simulation to kind of speed up this process. And this is something that is going to be presented at this workshop as well. And people are very excited about this direction right now. But we want to point out that while this gives us some computationally efficiency and sometimes does give us a better precision, it also has some problems. So for example, these are some of the differentiable simulation landscapes that you can get if you kind of naively code up the simple task here. So you need an expert knowledge in order to create differentiable simulators that actually have nice smooth gradients and landscapes. And so these differentiable simulation frameworks, they require a knowledge of frequently like a custom programming language or a framework, coding up custom physics equations, some non-trivial C++ Python integration and compiling, and also custom rendering tools. So this is kind of like very much work in progress in the community. So we want to also be able to actually have simulators that are scalable and that are easy to use for us, roboticists, but also that we can bring in other people, like for example, from computer vision, from machine learning, maybe from computer graphics and topology, and be able to kind of work with them all together using the benchmarking or simulation tools that are relevant to our tasks. And so this is one of the things that we've done earlier last year with a group at KTH, where we have a set of environments which are open source. They implement OpenAI Gym interface and they're fast, real time, built on PyBullet, but we have stylized them and kind of like customized them, pre-customized them, let's say, so that people are able to run them even if they're not roboticists or if they're just interested in a set of tasks and want to try something scalable, but they don't want to code up a physical simulation from scratch. And we've given some examples of how to load a very large number of mesh modifications into these environments. So for example, different garments and different data sets. For example, this 22,000 garment data set that's procedurally generated by another group. All All right, right. We have procedural generation of meshes and some interesting tasks on here that are just for exploring what one could possibly do with, let's say, interesting tasks for exploring what one can train with reinforcement learning algorithms and how far they are from currently being able to solve these tasks. So this is an example, even after extensive hyperparameter search of what a TD3 algorithm could do. And you can see it's not really achieving kind of like the goals here. And we also built in some experimental tasks here for us roboticists that would do dual arm manipulation and something like food packing tasks. So that's what we can do with non-differentiable simulators. And our next step right now is looking at mobile manipulation. So again, bringing in the deformables here. This is a visualization of AI habitat, which there are frameworks that are emerging right now that are good for mobile manipulation and navigation and so on. And they're highly visual, as you can see here. But in this system, they didn't yet have support for deformables. So this is what we're adding. And we want to do now the next step. After the real to sim, we want to do the sim to real with the robots that we have in our lab. All right, so to summarize, I've talked about first the distributional approach to encode the state of the deformables. And next, we would want to apply this to more general problems with partially observed settings, not necessarily focusing only on deformables. Then I talked about real to sim and that we can do this with differentiable simulators. And that there's some, to-dos in the community, even though there's interest. And also I talked about our work on large-scale training for interacting with people from other communities, but also bringing this to a more mobile manipulation setting, kind of whole room scenario as opposed to tabletop scenario. And these are the pointers to the work that I mentioned, and I would love questions from you.
Yeah, so if you have any question, maybe you can line up by the microphone and you might have to again repeat on.
Oh, okay. I will say something.
Yeah. Question.
Yeah, so this is cool. One thing I thought about the end really, like when you're talking about mobile manipulation as the next step, would you want to have a fully differentiable simulator like beyond so one thing I guess I'm trying to understand is you have to have a differentiable simulator for like this contact like modeling, right, for deformable manipulation. So how do you integrate that into like an existing simulator? And wouldn't you want like maybe multiple different types of modeling for differentials?
Right. So the question was, how would you integrate multiple different types of simulators together, and maybe one of them can be deformable and one of them can be even not deformable. Oh, sorry, not deformable, differentiable, and one can be non-differentiable. Usually the community that is interested in differentiable simulators, right, they see a lot of promise in it. So ultimately, I mean, you could in principle build there even right now, like the beginnings of the differentiable rendering, right, where you can, and actually, in part, that's what we're doing with point clouds, but people can do it with RGB as well. The problem is, of course, then scale. Can you really scale this? Can you really propagate enough radius through this whole thing? And I'm not sure about that. I'm a proponent of either a combination or also not leaving behind the black box simulators because they are fast. And gradients, they can be expensive, so it's not like they come for free. So I would say that for the cases where we really need precision, and for deformables, sometimes it is the case, right? Like you miss by only a little bit, and the band snaps, and you don't really put it on your pulse. For that, we might want a very precise model, and maybe we think very hard about that model. But for the whole room scenario, maybe you do want to keep your non-differentiable simulator that you're able to scale and stylize and everything. So in terms of on the interface, some piece that can use gradients and the other components don't use gradients, that's fine. But I think as a community, it would be nice to kind of not have the differentiable versus not argument, but more like bringing them together. I think that would be beneficial.
Thanks.
Thanks for the great talk. I'm wondering, when I look at graphics literature, there are some fantastic methods about like doing great discipline measures, fantastic visualizations, and then some motion models with blending and stuff. And then we have had some speakers today doing similar things with point clouds. And so both of their goals were to have the end result be similar. And your goal is to have the end those are way similar. So do you think you would have a distinct advantage in sample efficiency, or you also easier to train, harder to train, something like that?
Yes, thank you very much for this question. People don't normally notice. We tried using, for example, differentiable renderer. You would have to invest a lot of time in training that. So with, let's say, half a minute of work, I can import a texture of the object that I'm dealing with, right? And then spend a lot of time figuring out what the dynamics of this is. So in a sense, what we're saying is that in many cases, it is possible, like if maybe you don't have a whole room scenario, maybe you even have a tabletop scenario, it is frequently possible to bring the photorealistic part, even if you have to kind of load something by hand. You might not need to learn it from scratch, but after you have this, as a roboticist, you still have very little, because if your dynamics is different, right, you still cannot manipulate the subject. So that's why we focus on the physical parameters. And we say that it would be great. That's why we're like all up for collaborating with people in computer graphics, computer vision, all that, right? It would be great if there is some other component that would relieve us from the need to like load this, textures and so on. But as roboticists, we feel like, okay, but then we would still need to supply what is the right dynamics for this. And that's what we're focusing on.
So one more question, sorry. Can you please give some information about what was the exact role of the RKHS and the dot product and then expectation stuff? What was the exact equation for that?
Okay. So let's try to see if I can answer this quickly. Oh, yes. So I think the question was, so this embedding into RKHS, what is the physical intuition for it? All right. And I would say here that this is a very, very general mathematical method, right? So there is no direct mapping that I know of for like something that is related to physics, right? But our intuition here is in terms of the properties of what this gives. So if I go back and I say, oh, where was this? And I say, what do we want out of this? Why do we even bring this up? And there are these four things: permutation invariance, robustness to noise, convenient distance metric, and continuity, that this framework gives us automatically. And that's what we want. So it's not like we're saying that, oh, this is good for modeling some deformation model or some context or something like this, right? We're saying that it is a very general method that would take the representation that is noisy. So for example, we decided to extract key points. Oh, we could use something else, right? But that thing is, in its positional way, it's not robust to noise. If you permute the key points, then you kind of lose the interpretation of what this means. And what we're doing here is that we're bringing in this additional mathematical piece to say, okay, now with this piece, we don't need to worry about, what happens if we permute or what happens if there is noise. So that's the motivation part.
What is the convenient distance metric for? What is the convenient distance metric for your case when you are targeting that the sim and the real should behave similarly? So what is that distance metric look like?
That's not necessarily for sim and the real. That's even just for the states themselves, right? So if the rope deforms, right? If I see the rope as sort of like its surface as a probability distribution, right? Something that is far away in the sense has a very different shape. I should have like a natural distance metric that would let me tell that would let me say how different these two states are. And so that's what we get here, at least with the mathematical properties of it. But yeah, I don't think that you can have like a direct mapping to like 3D coordinates or something that is just more physical.
Thanks so much.
Thank you very much.
Thanks.